The second type here that we're going to talk today is called solid state ion selective electrode, or sometimes we call it crystalline selective electrode, because this solid state is in the crystal structure. So that's why we can call it both. So what is the solid state ion selective electrode? So this is constructed from the insoluble ionic salt of the analyte ion. Insoluble salt of the analyte ion. For example, if we want to measure the fluoride ion, as the example given here, if we want to measure the fluoride ion, then we can use some form of the solid state ionic salt of the fluoride ion. Solid state ionic salt of the fluoride ion, which here I put here that for fluoride detection they use something called lanthanum fluoride, LAF3. Now lanthanum fluoride is the insoluble ionic salt. By the term insoluble, it can actually soluble. It can actually like dissolve in water a little bit. So you may want to avoid them to be in contact with water. So what is the structure of this salt? So you can see here, it is the solid state or crystalline structure. So the cation and the anion is in the well order, like this is lanthanum ion. This is fluoride ion. So you get the crystal, right? But now, since you want to detect the fluoride ion, so you're gonna have to like fine tune the structure, like you make some vacancy in the fluoride ion so that you can bind small fluoride ion. And binding fluoride ion will give you that the membrane potential that we already discussed the last Tuesday. And the solubility equilibrium of this one is LAF3. You're gonna get like the LAF2 cation plus the fluoride ion. So if you have fluoride ion in the internal solution for one concentration, and if you have fluoride ion for the external solution or your test solution, then you can generate the membrane potential. This is similar to last time when we talked about glass membrane electrode. We have the internal solution with one pH and your test solution or external solution with another pH, and you generate the membrane potential. So same thing here, except that this fluoride electrode is made from the crystalline structure, crystalline ionic compound. And because this type of ion is made from the insoluble salt, but the term insoluble is actually like sparingly soluble. So we have to keep the solid state ion selective electrode in the dry air. You must not put it in the store it in the aqueous solution. This is in the opposite of the glass membrane electrode. For the glass membrane electrode, you have to put it in the aqueous solution all the time, right? So that you keep the hygroscopicity and the gelation and the ionic exchange process. But for solid state electrode, you need to keep it dry. You must not put it in the aqueous solution when you want to heat store it. So this is the principle of the solid state ion selective electrode. You have the crystalline insoluble salt of the ion that you want to measure. Here you want to measure the fluoride, then so you use the lanthanum fluoride, and you must keep it dry. And now this is the molecular ionic structure. So what is the electrode structure? So here you can see this. You can see that here you have the lanthanum fluoride crystal here at the end of the electrode. The solution inside it, you're gonna have the fluoride solution, of course, because we want to detect fluoride, right? So you want the internal solution having fluoride. So here they have the sodium fluoride. And then the outside, you're gonna put your electrode in the test solution, right? With another concentration of the fluoride. But you can see here that since you need two electrodes, right? So you have to have the internal silver chloride electrode as well, and that's why you need to mix it with the sodium chloride or sometimes potassium chloride as well. But this is why you don't really need to know the structure, but at least you should know in general this type of electrode needs the solution internal and external. But what you should know is the membrane potential of the electrode. I'm gonna go back a little bit. Where is it? So last time, I think, yeah, this one. Last time we plot the indicator electrode potential or the cell potential, which is E cell, and against the pH, which you get the negative slope. And you can derive this by yourself. For this one, for the cation, you get negative slope. For the anion here, which is fluoride, you get positive slope instead. And you can derive here, and you're gonna get something like membrane potential is equal to some constant plus the RT over ZF PF, but this is the form at 25 degrees Celsius, so you get 0.0592 PF. PF is minus logarithm of the fluoride, right? The base 10 logarithm. So if you plot the calibration curve theoretically from membrane potential against the PF, then you get the positive slope here with the slope of the 59.2 millivolt. This is millivolt per decade. So this is in opposite of the glass membrane. Glass membrane, you detect the cation, so the slope here is negative, but here you detect the anions. The slope here is positive. So if there is the question asking you to compare the response between the cation electrode and the anion electrode, you should be able to compare by using this. All right. Any question? What? How about the exam last Tuesday? Is it good or bad? Is it difficult or too easy? I want to know, because so that I can have the exam appropriately.
Normal?
Yes, medium.
It's mediocre. Okay.
Sorry?
Oh, what do you say?
Medium, like
Yeah, like not too difficult. Okay. Oh, okay. But I think your score in with everyone's score in before midterm is pretty good. I hate the true or false question. My exam has a lot of true or false questions, but we're gonna talk about that later. Since it is the blackboard exam, so that's one way to check your concept. But I think you're gonna be fine. So we will talk about the exercise or the quiz later at the end of the class. Okay. So this is the solid state electrode. This is for the anion, like fluoride. But there are some like operational or the good condition to operate the fluoride electrode and other solid state electrode. For example, like this is good if you go to be the lab manager and you want to purchase the new electrode for the lab, let's say, and you're gonna create like the specification of each electrode, like what is the good concentration range that you can use for that electrode, what is it made from, and what is the pH that you can use it, because one factor that affects the performance of the solid state electrode is the pH. So let's see the example. So we just talked about the fluoride electrode, right? So let's see the fluoride. So here we see that some example of the fluoride electrode has the good concentration range of the fluoride from 10 to the minus 6 to 1. So this is going to be translated into PF 6 to 0, right? And we just talked about the membrane material, which is lanthanum fluoride. The pH range, now this is interesting. pH 5 to 8. You cannot use the fluoride electrode outside this pH. Why? what's gonna happen if the pH is lower than 5? Can you guess? Why can't we use this fluoride electrode at the pH lower than 5? Is it gonna combine with the proton? So we need to know the pKa of the HF, right? The hydrogen, the hydrofluoric acid, which is about 4 or 5. So you are right. So if you have a too low pH, then your fluoride gonna be convert to HF. And since HF is not the same as fluoride, so now you're not gonna see it. So this is why you cannot use the electrode at the acidic condition to acidic condition. What about the higher than like pH 8 in the basic condition? This is a little bit hard. So if the pH is too high, then hydroxide may substitute the fluoride in the structure, because it turns out that fluoride and hydroxide have similar properties, right? At least they have a single charge, and then the size may be pretty much the same. So hydroxide can substitute the vacancy instead of fluoride, and that will contribute to the error in the measurement. So to use the potentiometric detection, you need to know the pH of the sample as well. So this is the example how to use chemistry to explain this kind of thing.